delighted to introduce Dr. Jim Hansen as our speaker. Dr. Hansen is head of NASA's Unit for Climate Study, the Goddard Institute for Space Studies. He also teaches Earth and Environmental Science at Columbia University's Earth Institute. This afternoon's talk will be entitled, What Determines Climate Sensitivity? And this evening at 8 o'clock at the University Center Ballroom, Dr. Hansen will give a talk entitled, The Threat to the Planet, How Can We Avoid Dangerous Human-Made Climate Change? Please join me in welcoming Dr. Hansen.
Thanks very much. I usually put on my title chart an asterisk with a statement at the bottom that it's my personal opinions. I'm not, although I'm a government employee, I'm not speaking for the government. And I didn't do that here because I thought I was speaking to some students in Steve's department about a technical topic of climate sensitivity, but the audience is a little, I guess, a little broader than I had expected. But I will be speaking more about the question of how sensitive is the Earth's climate. And I took a number of the charts from this evening's presentation, but I'm not really getting into the social aspect of climate change. But let me mention one other thing before I start. I was asked to make note of the fact that at 7 o'clock this evening, there's a rally called No New Coal, which is at the, does it say where it is?
University Oval.
The University Oval at 7 p.m. So, and I don't mind advertising that because one of the bottom lines from my discussion is that coal is the one place where we could, it's 80% of the solution if we would decide to use coal in a way that was environmentally friendly. Okay, now to talk about climate sensitivity, let me begin by, and Steve mentioned that if you have technical questions of clarification, you can ask me during the talk, and then, but for general discussion, probably wait until I've gone through my charts, and I don't have too many, so I should get through them. Okay, so a climate forcing. A climate forcing is a imposed perturbation on the planet's energy balance. So, for example, if the sun were to become 1% brighter, that would be a forcing of a little more than 2 watts per meter squared, averaged over the planet, because the Earth absorbs about 238 watts of energy from the sun. And a 2% change in the sun's brightness would be about equivalent to a doubling the amount of carbon dioxide in the atmosphere. Because if you add carbon dioxide to the atmosphere, that reduces the infrared or heat radiation from the Earth to space, because the carbon dioxide absorbs infrared thermal radiation and traps the heat radiation. And we can calculate that forcing very accurately. And another forcing, which happens to be of the same magnitude, is the volcano that went off in 1991. At about 6 months after the volcano, the sulfur dioxide gas that it injected into the stratosphere had all converted to sulfuric acid droplets, and that was spread around essentially the entire globe because the volcano was near the equator. And those aerosols reflected about 2% of the sunlight back to space. So it was a forcing of about 4 watts. Now, climate sensitivity is commonly talked about in terms of the Charney problem. In 1979, President Carter asked the National Academy of Sciences to look into this question of carbon dioxide and climate change. And so the Academy appointed a panel chaired by Jewel Charney at MIT to advise the government about this. And basically what Charney did was look at a specific problem, namely, what if you doubled the amount of carbon dioxide in the atmosphere? How much would you expect the Earth to warm up? But the way it was defined, it's important to note that, and this was investigated to some extent with models, and in fact the report that was written, they came to the conclusion that the expected global warming, at equilibrium, if you doubled the carbon dioxide and waited a long time, the Earth would warm up by about 3 degrees Celsius, which is about 5.5 degrees Fahrenheit, plus or minus 50%. So the error bar was very big, but that in getting that answer, the main tool that they had was some global climate models. There had been 2 models that had been run for that problem. One was Suki Manabe's at GFDL, and one was the model that we had run at our institute. And when Manabe ran his model, he got 2 degrees warming, and we got 4 degrees warming. And then they looked at the models and tried to figure out why did they get different answers. And you could see that Manabe didn't have very much sea ice in his model because his ocean was a little too warm. And our model got increasing clouds as the planet got warmer, while Manabe's model didn't have, it had fixed clouds, so they couldn't change. So anyway, there were different physical differences that could be understood, but we didn't really know which answer was closer. Anyway, they ended up taking the average and then having a big error bar. But you have to remember that the way the problem was looked at then was some other things were kept fixed. When models were run, the ice sheets on Greenland and Antarctica were fixed, were not allowed to change. And the vegetation distribution on the planet was fixed. And the greenhouse gases, the long-lived greenhouse gases, those were specified just by, all of them were fixed except CO2, and that was arbitrarily doubled. So they were not allowed to change either. What was allowed to change was those things in the climate system which would respond very rapidly to a changing climate. If the atmosphere becomes warmer, then it holds more water vapor. Just as in the summer there's more moisture in the air than in the winter. And the clouds can change quickly, and the sea ice can change quite quickly. But I think there's actually a much better way to estimate climate sensitivity. Because in models, you never know. The models now, I should mention, our model now gets about 3 degrees for doubled CO2. And that's sort of the center point. Models tend to get approximately that sensitivity. But you never know if you've got all the physics in the model. And you never know how well you can test some of the physics, but you're never certain how good the model is. I think the Earth's history provides a much better way, a way that gives us more confidence than the climate models, and actually it gives us a higher accuracy. And in particular, I like to compare the current interglacial period that we live in, which is now more than 10,000 years long, with the last ice age, 20,000 years ago. In each of these periods, if you average over a long period, 1,000 years or so, you know that the planet is in energy balance within a very small fraction of 1 watt. If it were out of balance by 1 watt, you would melt all the ice on the planet and raise the temperature of the ocean by 100 degrees if you were out of balance by 1 watt. So you know you're approximately in energy balance. And we can compare those 2 periods. The temperature difference between the ice age and the interglacial has to be due to forcings either within the atmosphere or on the surface, because we know the energy coming in is not changing on this short time scale. On the time scale of millions of years, the sun is getting slowly brighter. But on this short time period of 20,000 years, if you call that short, the sun's brightness is not changing. But what is changing, there are changes occurring both in the atmosphere and on the surface, and we know those. By the way, this curve here is the temperature in Antarctica as determined from an ice core drilled in the Antarctic ice sheet. The Antarctic and Greenland ice sheets are formed by snowfall piling up. It's too cold in those places to have any melting, so each year the snow just piles up deeper and deeper, and as it gets deep enough, the snow underneath gets enough weight on it that it's compressed into ice. And when it forms ice, it traps bubbles of air that existed at that time. So we can sample bubbles of air that existed for the last 400,000 years by drilling a core in the Antarctic ice sheet. In fact, there's now a core that goes back 700,000 years. And from the isotopic composition of the H2O in the ice, you can tell the temperature at which the snowflake formed. And that temperature varies by about 10 degrees between the warmest interglacial periods and the depths of the ice age. We can also take ocean cores and determine the temperature as a function of time. The composition of the shells of microscopic animals that lived in the ocean depends upon the temperature of the ocean water, and when those animals die and their shells sink to the bottom of the ocean, the sediments pile up, and just like the ice sheet, we can take a core of the ocean and determine the temperature. And what we find is that at the equator, the temperature difference between an ice age and the interglacial is about 3 or 4 degrees. And averaged over the planet, the change in temperature is about 5 degrees between the ice age and the interglacial period. And over that same time period, you can see that the amount of the long-lived greenhouse gases like carbon dioxide and methane, there's more of these gases in the warm interglacial period and less during the ice age. And we can calculate very accurately the climate forcing due to these changes in these long-lived greenhouse gases. And it amounts to about, let me see, this way. It amounts to about 2.5 to 3 watts per meter squared, adding up the forcing by all the long-lived greenhouse gases. The other big forcing is the change in the surface, which is mainly due to the large ice sheets that existed during the Ice Age. During the last Ice Age, there was an ice sheet that covered Canada and reached down and covered Seattle into Montana. I don't know exactly where the line was, but it even reached into Iowa and covered New York City. There was so much water locked up in that ice sheet and a smaller one on Eurasia that sea level was about 120 meters, about 400 feet lower than it is now. But there were also changes in the vegetation distribution on the planet, and the outlines of the continents were different because sea level was so much lower, so the continental shelves were exposed. But all those changes together, the main effect was the change in the area of the ice sheet. And during the Ice Age, the reflection of sunlight by the ice sheet reduced the heating of the planet by about 3.5 watts per meter squared. And so the total forcing was about 6.5 watts per meter squared, and that maintained a planet that was 5 degrees colder. So that implies a sensitivity of about 3/4 of a degree for each watt of forcing. And if you make a 4 watts of forcing, that's 3 degrees for doubled CO2. So it happens to agree very well with what we get with the climate models, but the error bar on this is somewhat smaller. And furthermore, we know very well that the real world includes all the physics, and it does it correctly. And we're never sure about the climate models. Now, let me see. Okay. Yeah, as I mentioned, the sea level, yeah, so that estimate for sensitivity is derived from just comparing 2 points in time, the Ice Age and the interglacial period. But now we can actually check that climate sensitivity for the entire 425,000 years of the past 425,000 years, because there is a record, there are several different records for the sea level change during this period of 400,000 years. And as I mentioned, sea level change is more than 100 meters between Ice Age and interglacial period. Well, the water that's not in the ocean is on the land in these ice sheets, and the size of the ice sheets is going to go, the ice sheets grow both in all 3 dimensions, both horizontal dimensions and in thickness. So roughly speaking, the area of the ice sheets is going to go like the 2/3 power of the volume of water. And so we can calculate, knowing the forcing for 1 point in time, we can calculate the forcing at any point in time. And the forcing due to the change in the sea level is calculated as the blue curve. And the greenhouse gases, well, we know those very accurately from the ice cores, so we can calculate the climate forcing due to the greenhouse gases. And if we just add up those 2 forcings and multiply by 3/4 of a degree for each watt, we get a estimated temperature change given by the blue curve on the bottom. And you can see that that agrees very well with the observed temperature change, where I've taken, for the observed temperature change, I've taken the Antarctic temperature change divided by 2, because the amplitude of global mean temperature change is about half of that in Antarctica. So that tells us that this climate sensitivity is actually quite general, and gives us increased confidence in it. And now there's an interesting aspect of this, which always causes a great deal of confusion, and that is the fact that if you look carefully at the greenhouse gas changes and the temperature change, you see that the temperature changes first. If you look here, I've plotted the greenhouse gas forcing by the 3 long-lived greenhouse gases and the Antarctic temperature on the same graph with different scales. And well, the one thing to note is they're in remarkably good agreement. But if you look very carefully at how they correlate, you find that the temperature leads the greenhouse gas forcing by several hundred years on the average. And this is our best chance to correlate them. Even in this case, there's error in trying to get the timing of them, because as this snow piles up, as long as you still got snow on top of the ice sheet, the air is mixing through the snow. It's not until the snow gets about 100 meters deep that it's sealed off, that the bubbles are sealed off in ice. And it takes of the order of 1,000 years to get this enough snow on top. So you've got that error, and the rates of snowfall change as the climate changes. So you don't have a, but but nevertheless, it's clear. And I think there will be this should be proven by the new ice core that's been taken in Maudland, Antarctica, because the snowfall rate in Maudland is about 10 times, is much higher than it is at the South Pole. At the South Pole, it's so dry, it's such a dry desert that the amount of snowfall per year is very little. But anyway, so that, but the point is, keep pointing the wrong direction. Yeah. But the thing is that the greenhouse gas change and the albedo change, those are the mechanisms causing this huge climate change as a function of time. But they are not the instigator of the climate change. The instigator of these regular climate changes are changes in the Earth's orbit. But on these sort of timescales, the mechanisms for the temperature change are practically simultaneous with the climate change. Now, what's actually happening, the most important of these orbital parameters is the tilt of the Earth's spin axis relative to the plane of the Earth's orbit. Right now, the Earth is tilted at about 23.5 degrees to the plane of the orbit, but it wobbles by plus or minus 1 degree about that angle, and it does it with a very regular periodicity of 41,000 years. And if we look at, let's focus on the middle. I have a temperature, I have a curve here. This is from one of the ocean cores that I talked about, or it's actually from the average of ocean cores all around the oceans, many different places in the world's oceans. And what it is the oxygen isotope in the shells, these foraminifera, which are these microscopic shelled animals. And the amount of oxygen 18 is a function of the temperature at which the animals were living. And that's the only thing that it is a function of as long as there's no ice on the planet. And this is, by the way, this is a record that goes back 65 million years. So, 65 million years ago, there was no ice on the planet. It was much warmer then. The ocean was at 10 degrees Celsius instead of 0 degrees Celsius. These are benthic foraminifera, which live near the ocean bottom. And, but the ocean bottom was about 10 degrees Celsius while it's 0 degrees today, and it actually got warmer for a while. And it wasn't until 35 million years ago that Antarctica started to get, there were some small ice sheets on it, but then suddenly at 34 million years ago, it got entirely glaciated. And once you start to have ice on the planet, then this quantity depends on the amount of ice on the land, because oxygen 16, which is lighter, evaporates from the ocean more readily than oxygen 18, and so the ice sheets are oxygen 16 rich, and the remaining water in the ocean is then depleted in oxygen 16, so that increases this oxygen 18. So, but then both the accumulation of ice on the continents and the decreasing temperature drive it in this direction. So for the entire curve, it's a relative measure of temperature. And anyway, now I've blown up the last 3.5 million years and shown that here. And the planet during that last 3.5 million years has continued to get colder, but you can see the temperature is oscillating regularly. And in fact, if you look carefully at this, for most of this period, the period of those oscillations is a very regular 41,000 years, because what happens is when the tilt becomes larger, you're exposing the ice in Antarctica to more sunlight, and it melts the ice. And at the same time, 6 months later, in the northern hemisphere summer, you melt any ice. You tend to melt any ice in the northern hemisphere. So therefore, it's a very, in both hemispheres, the forcing is the same. And so you get this very regular fluctuation. The amount of ice increases and decreases with 41,000 year periodicity. Well, it became more complicated in the last million years. As the planet got colder, then we got to the point where we had this large ice sheet in North America, this Laurentide ice sheet, which covered Canada and reached down into the United States. Well, there could not be a similar ice sheet in the southern hemisphere, because if you look at the southern hemisphere, it's all ocean at that point, and you've got this roaring ocean waters going around. So it became a very asymmetric situation. And then there's another orbital parameter that comes into play if it's asymmetric, and that is the fact that the Earth's orbit is sometimes circular and sometimes elliptical. It's in general elliptical, but the ellipticity keeps changing because, by the way, all of these orbital parameters, the reason that they're changing is because the planets, the other planets are tugging on the Earth, and depending on how close the Earth comes to the other planets, it makes these small perturbations to the Earth's orbit. Jupiter and Saturn, because they're so heavy, are the main culprits, but also sometimes the Earth and Venus get quite close together. Anyway, but so these changes in the Earth's orbit this is a completely deterministic problem. You can solve the equations of motion with Newton's laws and get these changes in the Earth's orbit very accurately. But what now happens in the last million years? Today, the eccentricity of the Earth's orbit is not too large. It's 1.6%. Sometimes it's as much as 6% is the maximum eccentricity of the orbit. But we are closest to the Sun in January and furthest away from the Sun in July. So that's a situation that dampens the seasonal cycle, makes the winter relatively warm because we're closest to the Sun again. And that means our winters are a little bit warmer than they were on the average over the last 100,000 years, which is good for getting more snowfall. And in the summer, since we're furthest from the Sun, that's good for preserving. It keeps the summer cool, so you might, if you start to build an ice sheet in northern Canada, it might be able to survive the summer. So we would have expected, that we would be headed toward the next ice age. We've been in this warm interglacial period for more than 10,000 years. But the reason that but that phenomena, if you think about it, and I shouldn't spend any more time on it, but in the southern hemisphere, it's just the opposite. So although we would be building an ice in the northern hemisphere, we'd be melting it in the southern hemisphere. And as long as you've got comparable amounts in the two hemispheres, you don't get much effect. But now, in the last million years, because we had this huge ice sheet in the northern hemisphere and not nearly as much in the southern hemisphere, these other parameters come into play. The eccentricity, which varies with 100,000 year as a primary periodicity, and the precession of the equinoxes, which is what tells us which day in the year we're closest to the Sun. That changes with the 23 100,000-year periodicity. Anyway, these orbital parameters are what drives these fluctuations. And but then the mechanism that actually causes the temperature change are the greenhouse gas changes and the ice area changes, with the changes in this sunlight amount driving those mechanisms. But because that's a little complicated, I think it might be useful to look at another situation, which, if we look at, why doesn't this guy, am I pushing the right button here? This must like this one for some reason. I can go backward. Now let's see if I can go forward. There we go. Oh. Well, as I mentioned, this is a little different than I thought. But we now, humans now control these mechanisms for climate change. The greenhouse gases are now increasing off the, completely outside the range that's existed for millions of years. This is CO2 and this is methane. So we control the mechanisms for climate change. I thought that I'm having trouble with your technology here. I want to talk about one more piece of paleoclimate data, because you know, what's happening on the million-year timescale or the 100,000-year timescale, the reason that carbon dioxide amount in the atmosphere is changing is because there's a movement of carbon dioxide between the different surface reservoirs of carbon dioxide in the atmosphere, in the ocean, in the soils, in the biosphere. The carbon dioxide can move among these reservoirs. And in fact, the primary one is simply the fact that as the ocean gets warmer, it gives out more CO2. Just the solubility of carbon dioxide in water decreases as the water gets warmer. That's why your Pepsi loses its fizz. But because this is a little complicated, the movement of carbon dioxide among the different reservoirs, we can look at longer time scale when there's a simpler relationship between the amount of carbon dioxide in the atmosphere and the climate. If you go to long time scales, then you can get an exchange of CO2 between the Earth and the surface reservoirs. The mechanisms by which CO2 is taken out of the surface reservoirs there are two mechanisms. One of them is weathering, primarily of silicate rocks, where water and carbon dioxide or carbonic acid, and anyway, as weathering occurs, the net product of that is deposition of carbonate sediments on the ocean surface. And that takes CO2 out of the surface reservoirs on long time scales. The other mechanism is the deposition of organic material on the ocean surfaces, and where you're burying organic material, some of which forms fossil fuels on the long time scales. The mechanism by which CO2 is returned from the Earth to the surface is basically volcanoes and related phenomena, the springs with seltzer water, in effect, seltzer springs. These are all caused by the subduction of oceanic plates as a continental drift occurs, and as ocean crust goes under the continents, the metamorphic processes, the pressure and high pressure and temperature on this subducting ocean crust changes the rock type from the carbonates to basalts and other kinds of rocks, but it releases CO2, which comes out in volcanoes primarily. But, you know, if you look at the continental drift over the last 250 million years, I like to particularly focus on the period from the end of the Cretaceous to the present, because by the end of the Cretaceous, the okay, I'll come over here. There we go. Okay, I think I figured it out now. I have to be right there. Okay, so the end of the Cretaceous is the beginning of the Cenozoic era. And the thing is that climate forcings either need to be something coming from the outside. Now we know that the sun was dimmer then by about 0.5%, which is a forcing of about 1 watt per meter squared. And we know that by that time the continents were very close to their present latitudes, even though their positions were not quite the way they are now. But that difference is only enough by the albedo effect to cause a forcing of the order of 1 watt per meter squared. But the amount of CO2 in the atmosphere changed by large amounts. 50 million years ago, there's between 1,000 and 2,000 parts per million of CO2 in the atmosphere. But in the recent glacial to interglacial cycle, CO2 has been going between 180 and 280 parts per million. So there's more than 3 doublings of carbon dioxide between the low amounts and the high amounts. And that's a forcing of more than 10 watts. So that is dominant. The atmospheric changes are clearly the dominant climate forcing on these long time scales. And that lets us look at the question of, basically what is happening in this period up until 50 million years ago, the so-called Tethys Ocean between India and Asia, between Africa and Eurasia, was closing. And the ocean crust, the carbonate-rich ocean crust, was being subducted, and the CO2 in the atmosphere was increasing, and the planet was getting warmer. But at 50 million years ago, and I should have mentioned that the interesting thing about this was 65 million years ago, India was still in the South Indian Ocean, but it was moving north at a rapid rate of 15 centimeters per year, which is half a foot per year. Eurasia was retreating at a rate of about 2 centimeters per year, but then it got rear-ended by India with a tremendous crunch 50 million years ago, and that has been pushing up the Himalaya mountains and the Tibetan plateau, and that's causing a huge area of strong weathering, which draws down atmospheric CO2. So what we see is that so 50 million years ago, when India crunched into Asia, CO2 began to decrease and the planet began to cool off. And then it reached a point where Antarctica froze over. And that actually caused some negative feedbacks, because then you got no more weathering on Antarctica. Antarctica is covered by ice, it can't weather. And there's also upper Alps were also sort of the product of the African plate getting close to the Eurasian plate. But eventually, and the details of the ups and downs here are not necessarily understood, but I think what's happening in the last 15 million years, when things have really started cooling off again, is the Andes Mountains have been growing very rapidly in this period. We have data showing that the Andes have been rising at a rate of about 1 millimeter per year. which is 1 kilometer per million years. And so that makes for a lot of weathering. And it's, in fact, it's and the mass of the Andes Mountains has been increasing so that the subduction, which has actually slowed down the subduction of the ocean plate under the South American plate by 30%. So that reduces the CO2 emissions to the atmosphere also. So both because of increased weathering and reduced subduction, we've got CO2 decreasing, being drawn down. And so other things being equal, you know, the Earth is really headed, has really been headed downward. And as it gets colder, these amplitudes of these ice ages gets bigger, has been getting bigger and bigger. Anyway, I'm now working on a paper in which we quantify, unlike the case the last 400,000 years where we have these great measurements of atmospheric composition, we don't have that for the very long time scales. But there are some proxy measurements for CO2. Which are not very accurate when the CO2 amount is small. So, but at some of these times in the past, now here I have actually a graph going back 600 million years, and you can and then this second part shows when this second part shows when this was the really extensive ice age 300 million years ago. And in fact, the ice went all the way down to 30 degrees latitude. And there was very little CO2 in the atmosphere then. And in fact, and also, as you go back further in time, this is now long enough time scale. So the sun was 3% dimmer at this time and 6% dimmer here. But I don't have yet the finished product, but I can say that this is also consistent with the climate sensitivities that we get from the other timescales. And this doesn't have the problem of this phasing, which of the temperature and CO2 change, which throws some people off. Let me get over here, and there we go. Now, if we can also let's look at a time period that may be more familiar to you, like the last century. And if we want to look at that short a time scale, then we have to worry about the response time. What we've been looking at is the long-term equilibrium response to a given forcing. But if we look at a century time scale, then we have to worry about the fact that if you apply a forcing, the ocean has tremendous thermal inertia. It doesn't respond immediately. The response function for the ocean looks something like this. If you suddenly introduce a forcing, say we double the amount of carbon dioxide, then the ocean starts to warm up, and this is going to be its 100% response. Well, after 20 years, it's got almost half of the response, but then it slows down. And it's not until 1,000 years later that you've got the full response. So you have to take account of this thermal inertia of the ocean. And you also have to take account of the fact that CO2 is not the only thing going on. If we compare today's climate, today's atmosphere with pre-industrial, then CO2 has increased enough to cause a forcing of 1.5 watts. But methane and its effect on stratospheric water and tropospheric ozone causes a forcing of about half that large. And then there are the chlorofluorocarbons, there's nitrous oxide, there's tropospheric ozone other than that, which is here, and there's black carbon, soot, black soot, but there are also negative forcings because of the small particles that come from burning fossil fuels, mainly sulfates. And then these particles, both the black carbon and reflective aerosols also affect the clouds and tend to increase the cloud cover. So that's a negative forcing. So we have to try to take account of all these forcings, and we can do that in there's some small, each forcing is not exactly equally effective. So you need to take account of the fact, you need to explicitly model the different forcings because some are a little more effective than others for the given watts per meter squared. But anyway, that's done automatically in the global climate model, which explicitly includes all of these forcings. And these are our estimates for all of these forcings. The biggest forcing is the increasing greenhouse gases. But then there are volcanoes that go off. This was, forget the name of that volcano, Krakatoa. And then this was Pinatubo, and this was El Chichon and Mount Agung. But then there are also these aerosols, the human-made aerosols, which give a negative forcing, and that one is very uncertain by at least 50%. But anyway, taking our best estimates for all of these, putting them into a global climate model, which has a global ocean model, so its response time is there, then it turns out that the model does quite a good job of reproducing the observed temperature change over the last century. Each time you run the model, you get a different answer because of the chaotic nature of weather and ocean dynamics. But basically, it's in pretty good agreement. And this is a climate model that has a sensitivity of 2.8 degrees Celsius for doubled CO2, so approximately 3 degrees. Now, we might have got equally good agreement if we had used a higher sensitivity and a smaller forcing. But the sensitivity, I would argue, is strongly constrained by the paleoclimate data. So I think this is probably more or less the right answer for the right reason. But and then we can use these same models to project into the future. And if we follow business as usual increases in greenhouse gases, we're going to get a temperature increase of a few degrees Celsius in the rest of this century, which is going to make it a totally different planet than anything that humans have experienced. I've tried to define a scenario that would keep the warming less than 1 degree because I argue on looking at the history of the Earth that we had better keep the warming less than 1 degree or we are in big trouble. Why am I showing that again? I think if we look at prior interglacial periods, there were some interglacials that were warmer than the Holocene. And I don't have the graph here, and I will talk about the climate impacts and what needs to be done about that in my talk tonight. This talk was meant to just focus on the question of climate sensitivity and how we know that our climate sensitivity in models is about right. And that knowledge is based mainly on the history of the Earth. But I will show that with the present warming that's occurred, we're now within less than 1 degree Celsius of the maximum global temperature of any interglacial periods in the last million years. And there are reasons we'd better stay there. Even those interglacial periods, the warmest of those had sea level a few meters higher. But if you want to go to a planet that was 3 degrees warmer, which is what we will get with business as usual, the last time the planet was that warm was 3 million years ago, and sea level was 25 meters higher. There was no sea ice in the Arctic in the warm seasons, and it was a very different planet. But and I think one of the points I will make is that there's a large gap between what is understood about global warming by the relevant scientific community and what is known about global warming by the public and the people who need to know, the public and policymakers. Because our knowledge of climate sensitivity is very solid. There's really no question about that. And our knowledge of the changing climate forcings is very good. And we are setting the planet on a trajectory which has very dramatic consequences on the time scale even within this century. But I think I'll stop here and I'll take questions if you like.
Skeptical critics have gone from denying that there are problems to suggesting that there may be easy technological fixes that can be discovered. Could you say a little bit about how likely it is that such technological fixes can be developed in a safe way so that we can continue our affluent way of life while maintaining the stability of the planet?
Well, I think there are technological fixes that would reduce the forcing and would in many ways improve our lifestyle. Because we have to get to a world beyond fossil fuels at some point. We're already close to peak oil production. We're going to run out of oil. Coal could last longer. But at some point we've got to come up with energy sources that other than fossil fuels. And it would make enormous sense to do that sooner rather than later, because that way we could avoid the climate catastrophe, and we could also get a clean atmosphere. And right now our fossil fuels are also polluting the ocean. We're putting mercury in the ocean at a rate which is going to make some fish inedible. So the technological solutions which would be unleashed if we put a gradually increasing price on carbon emissions could solve the problem, I believe. I don't believe if you're suggesting geoengineering. I mean, we are geoengineering right now. We're changing the composition of the atmosphere, and that is geoengineering. But the other technological solutions, like putting some shades in the space to reduce the sunlight hitting the Earth, that technically you could cool the Earth that way. But if you look at the price of getting that big shade into space, it really doesn't seem it's so much easier. There are many things that we can do now which actually have zero cost and which reduce the magnitude of the forcing. There are energy efficiencies which could pay for themselves, but we're just not encouraging them to happen. So I think the solution is technological, but it's got to be spurred by the public, because it's not going to happen if we wait for politicians. Politicians are too much under the influence of special interests. They get too much of their campaign contributions from fossil fuel industry. They just aren't going to take the difficult steps unless the public gets annoyed about this and makes clear that it's an issue that matters to them. And so I think the technological solution is possible, and there are, I think the potential of many renewable energies and things is really, we don't really know. That it's hard to predict exactly where the technological solutions are going to be. If you try to compare today's technology to 100 years ago, we couldn't have imagined the things we have now. And it's hard to imagine what we'll have in 100 years. But we need to spur that effort.
What is the model used for the circulation of water within the oceans? Can you speak about where the historical data that drives that part of the model comes from?
Well, the ocean circulation comes naturally just as the atmospheric circulation does. Both the atmosphere and ocean, you just have fundamental equations for energy conservation, momentum conservation, ideal gas law, and it's the atmospheric part of the model is just a weather model, but it'll run for a longer time period. And so you've naturally got the ocean atmosphere and ocean circulation just from the fundamental equations. You can start out with the atmosphere and ocean totally at rest, and then just apply these equations and run the model, and after a while you see the atmosphere moving the way the real atmosphere moves, and you see the ocean circulation moving the way the ocean circulation does. Not the ocean circulation models, you know, the resolution is fairly crude compared to some of the little circulations within the ocean, but basically the models do quite a good job without putting in anything to force it other than the sun.
Since you've talked to a lot of people around this country, what are some of the, and average people at that, what are some of the biggest misconceptions that people have about the science?
Misconceptions about the science.
Well, you said that
Well-
lag was one of those things. People have a big misconception about the lag.
Oh, you know, I think one of the misconceptions, and many of these are still misconceptions of even some scientists. An important thing, I showed you the response time of the ocean's temperature to a forcing, but an even more important or equally important response curve is what happens to carbon dioxide when you put it into the atmosphere. I was just talking at lunch, and somebody asked, isn't it a 50-year time constant that it will disappear into sink in 50 years? Well, the sinks for carbon dioxide are very interesting. And what happens if you put a pulse of CO2 into the atmosphere by burning some fossil fuels, for example, that pulse decays quite rapidly, so that within about 25 years, half of it is gone. And then the curve goes like this, and after 100 years, you still got 33% left. And after 1,000 years, you still got 20% left. So the reason is that the major sink for the carbon dioxide is the ocean. The ocean is taking up part of that CO2, but then the CO2 in the ocean, in effect, exerts a back pressure on the atmosphere. And you're not going to get all of the CO2 in the atmosphere to get into the ocean until the CO2 that you've already put in there sediments out as carbonate sediments, and that takes thousands of years. So that's the basic problem, which is not well understood, and it has a huge implication. It means that if you look at the amount of carbon in oil, gas, and coal, you see that the oil and gas, which has smaller amount than coal, is enough to get us up to at least the dangerous level, and probably somewhat beyond the dangerous level. And it's going to be very hard to prevent emissions of those CO2 molecules from oil, because you can't tell Russia or Saudi Arabia, don't drill your oil. You know they're going to do that, and it's going to be used in the mobile sources, vehicles, and it's going to come out the tailpipes, and you can't catch it. But coal has much more CO2, and it would be practical to capture the CO2. If you decided, okay, we're only going to use coal at power plants which have capture and sequestration, that's 80% of the solution. That's why I say the most important thing that's needed now is a moratorium on any construction of any new coal-fired power plants unless and until you capture the CO2. And if we would just agree to that, and if we would then agree over the next few decades linearly decrease, linearly phase out, bulldoze the old coal-fired power plants until there are none of them left in 2050, then CO2 would never reach 450 parts per million, because there's not enough in oil and gas for it to do that. And so that's the biggest part of the solution. And people will say, well, India and China are never going to agree to that. Well, they will within a decade. Once we see some more climate change, and they're going to suffer more from the climate change than we will, because China's got 300 million people living within 25 meters of elevation of sea level. And the regional climate changes there are big also. And this, you say, oh, that's a very big job to replace all these coal-fired power plants. Well, compare it to the energy effort that we put into World War II. It's not that difficult. Could be done.
Have you had an opportunity to discuss this with our governor? He seems to be more or less on the same page as you are, but...
Yeah, be careful to, the answer is I have not, and be very careful what politicians say. And compare what they say and what they do, because it is one thing to say that you're in favor of sequestration, carbon capture and sequestration, but that means you should have a moratorium until you have that technology. And that technology is not free. It's going to, it will increase the cost of coal-fired power substantially and make energy efficiency and renewables and other competitors more competitive. And so if they really mean that, then they've got to stop building those plants that don't capture the CO2.
With the sequestration of CO2 and liquefaction of it at 2,500 feet or whatever it is, do you think that's going to change circulation and the reintroduction of more CO2 into the atmosphere via volcanoes or oceans?
No, the sequestration, the one, there had been talk about putting it in the bottom of the ocean or something. That'll never happen. People will never allow that to happen. You don't know what the consequences of that would be. But where it would be out of harm's way and inherently stable would be underneath ocean sediments at a depth where the pressure and temperature is such that it is inherently stable. It's not going to try to escape. But that's, we may have to pipe the CO2 to the coastline and do that. But of course, you can also just put it in there are geologic reservoirs where the scientists, the relevant engineers are quite confident that it would be stable. And that is, on small scale, that is occurring as oil companies will inject CO2 into old oil wells to enhance the recovery of oil from the wells, but it does seem that the CO2 does stay down there. So as long as the one problem that's been pointed out is there have been so many holes punched in the surface looking for oil that you have to be careful that you don't put the CO2 in a place where it can get out those holes, because you could plug the holes if you know where they are. But under the ocean sediments, it would be inherently stable.
You're specifying or stating pretty much on sequestration. Of course, the cost of that leads to the question, what do you feel about wind and solar and wind for hydrogen as major components and not even get into the carbon sequestration?
My guess is that I don't think you can just say we're not going to use coal, period. But I think you can force it to compete. And my guess is that most of it will get left in the ground. There are other disadvantages to coal. I don't know how they mine coal here, but in the east they take the top off the mountains, and then they end up with all this junk going in the streams, and it's really pretty destructive process. So On the other hand, there's a lot more energy in coal than these other fossil fuels, and unless we come up with some other things, it may very well be used. I just think that we have to insist that if it is going to be used, that it be truly clean coal, not just in name, the way some politicians say, but it has to really be clean, and that means no CO2 emissions, and also no mercury and the other things.
Would you care to comment on the possible change in the ocean circulation going up along the east coast of the U.S. and the Earth?
Yeah, that question of the impact of climate change on the ocean's thermohaline circulation and particularly the transport of heat by the ocean to the North Atlantic Ocean, that aspect of climate change got greatly overblown into some complete nonsense in science fiction, in the science fiction movie. But it is true that in the Earth's history there have been times when this thermohaline circulation shut down or slowed down greatly, and that does have an effect on the transport of heat to the North Atlantic and some effect on European temperatures. But that phenomenon is seems to be well simulated in the global atmosphere, ocean, and climate models. And the global warming that's going to occur, and has already started to occur, that phenomenon causes the warming in the North Atlantic to be very small. And in fact, there's even, in most models, we have a small area which actually has cooling. And that may very well account for why Greenland has warmed less than most of the world. But it doesn't cause extreme cooling. It did cause strong cooling in the natural world when it shut down because the positive feedbacks worked to amplify that. But now the globe overall is warming, and the overall feedbacks are all therefore positive. So what it does is slightly reduce the warming in Europe, but still Europe gets warmer. But it's not insignificant phenomenon, but it's a rather minor aspect of the global warming story, rather than the dominant aspect that it has sometimes been portrayed to be.
Is the treatment of vegetation a weak point in your body?
Yeah, the treatment, that's actually the vegetation, as I mentioned. Oh, you know, I forgot an important point. The climate sensitivity, I forgot. I started out saying I was talk first about the Charney climate sensitivity. But I said Charney fixed the ice sheets and the vegetation. Now, we can use the real world data to estimate what the climate sensitivity would be if we did not include that constraint. And that's actually shown by one of my curves. That may be why I had that chart there and I forgot about it. Let's go back fast enough. Okay, here is an empirical relation. You can see the greenhouse gas forcing and the Antarctic temperature change. The change in the temperature with the greenhouse gas forcing is 6 degrees Celsius. 12 degrees Celsius for 4 watts of forcing in Antarctica, or 6 degrees Celsius global average with 4 watts of forcing. 1.5 degrees with 1 watt of forcing. So that's twice as large as the Charney sensitivity. Because this is really the situation that we're dealing with now. The greenhouse gases are the forcing, and the ice sheets will respond with some time scale which is debated. I argue that that time scale is decades to centuries, that the ice sheets cannot survive more than centuries. There are some people who thought that ice sheets can survive millennia. Well, with the human forcing, which dwarfs the natural rates of change of forcings. I cannot see any way that ice sheets could survive more than a few centuries. And I would say that within 1 century, if we go business as usual, you are certainly going to see substantial ice sheet disintegration, because the summer melt season is getting stronger and longer, and the amount of melt on the ice sheets on West Antarctica and Greenland has been increasing rapidly. If you allow the ice sheet, so what this shows that over the time frame, over the last several 100,000 years, when the ice sheets were at some times quite large, so that feedback was quite strong. Now, as we go into the future, and eventually, when the ice sheets go away, well, then the ice sheets are not going to contribute to this forcing, the feedback any longer. But there's still a lot of ice on the planet, in Greenland and Antarctica. So I think this estimate of 6 degrees sensitivity for double C is more relevant to the time scale of hundreds of years, rather than the Charney sensitivity. And not only, now back to your vegetation, not only can ice sheets change, but the forests can change, and there is some movement now of forests toward the higher latitudes, but also because of the nature of the climate change, on the short time scale, we're actually destroying a lot of, there's some of the forests which just can't survive with the climate change. So I think the equilibrium response will be a greener northern hemisphere, but it may take a long time to get there, because you've got to have a different kind of vegetation get introduced. It absorbs a lot of sunlight, and if you replace tundra regions with vegetated regions, that's going to be a positive feedback.
How does nuclear fit into this? How do you feel about that?
I think that's nuclear is a potential, is one way to reduce CO2 emissions. I think it has to be a local or regional decision. So, for example, France is comfortable with nuclear power, and they get most of their electricity from nuclear power. Their next door neighbor, Germany, has decided to get rid of nuclear power altogether. And that's okay, except that Germany is now going to build coal-fired power plants. And and even though they have, in a sense, the greenest government of anyone, they're willing to pay a lot more for their energy to try to make it environmentally friendly. But they don't seem to get it, because as I tried to explain, the CO2 molecules from coal are different than the oil and gas. The oil and gas is going to get there anyway. But coal is the one thing which we cannot afford to continue to put it up there, because we can't take it back once it's up there. So we've got to make the decision, we're not going to use coal unless we capture the CO2. And so they don't get that. So back to your nuclear thing, well, I think it's from a climate standpoint, it's friendly. There are still problems with nuclear. I think the waste disposal problem is a technical one that's solvable. But the proliferation of weapons-grade material is a problem. It's probably also technically solvable. And as a physicist, I would much prefer to live next to a nuclear power plant than a coal-fired power plant, because I know that many thousands of people have been killed by air pollution, but not very many from the nuclear power.
Is there an appreciable component of this in the burning of non-sequestered carbon?
I don't quite understand the question.
What's happening to this? Something goes up here in this part of the country all the time. Forest fires.
Oh, yeah. Yeah, well, presumably the forests will grow back, and so the net emission on the long term is zero. But you'd really like to have healthy forests, because the forests and the soils can sequester CO2. And if we change the climate such that the forests burn and soil actually loses part of its carbon, then it's contributing to the problem rather than to the solution. I'm actually optimistic that we can solve this problem, because if you look at, given each year, if you look at how much CO2 we put into the atmosphere by burning fossil fuels and look at how much is added in the atmosphere, you find that the increase in the atmosphere is 57% of the amount that we put up there. So the other 43% is being taken up, mainly by the ocean. But if we would just stop putting the coal portion up there, we would have a large part of the solution. But in addition, if we would improve our forestry and agricultural practices so that the soil sequestered more CO2 and we stopped deforesting and getting a positive input from the forests, then we could solve the problem. So far, we've been moving in the wrong direction, and we've got to change that direction.
Can you estimate the cost of sequestration, the percentage cost? Because the conservative critics of a technological fix, an easier fix, would have us believe that we shouldn't pursue your approach, because every other air pollution problem has turned out to be easier to deal with than we thought it would be at first. And so they're arguing there will be some cheaper approach.
No, that's not inconsistent with what I'm saying. I'm saying put a price on carbon emissions, and those easier approaches will come. That's why I say I'm not recommending carbon sequestration from coal. I'm just saying that if we do use it, so that can be one of the competitors, but it has to compete with wind.
I'm not disagreeing with your position. I'm just trying to get a sense of what you think.
Right. But now so your original question was how much will sequestration increase the cost of electricity from coal? And according to, I'm not an expert on that, but according to the experts, if you once get this down and you start producing many units, it may be only 25%. But at the beginning, it's going to be more than that. That's what they say.
I'm afraid this will have to be the last question.
Dr. Hansen, lacking the political will to conserve in this country, what are your opinions on these two questions? One is the more efficient combustion of coal, and secondly, the work that the Germans are doing on mineral accretion in the oceans.
The more efficient, it is true that some of the old coal-fired power plants are not the newer technology. You can get an improvement. The efficiency is something like 30%. Some of those in China like 25%, and you could have 35%. So in that sense, comparing 35 to 25, it's a pretty big reduction of a quarter or so in the amount of CO2 for the same amount of energy. So those things it can help, but they can't solve. It's no solution to the problem I'm talking about, because go back to the bar graph that I never showed, but the bar graph for oil, gas, and coal doesn't matter if you're making that energy that you get out of the coal more efficiently. If you're still going to use all this coal, it's the same amount of CO2. You're just getting more energy out of it. So it doesn't really help. It just slows down a little bit the rate at which you put it up there, but since it stays there 1,000 years, it doesn't help much. And I didn't understand the last half of your question.
The Germans are doing research on mineral accretion in the oceans, where they have very small influx of electron movement, and they can tie up calcium carbonate in the oceans to the tune of approximately 300 to 400 million tons of carbon a year.
Well, that's the natural sink. I mean, forming carbonates in the ocean floor. That's what happens on the 1,000-year time scale. That's why I say it stays for 1,000 years. So if you can speed that up, that would be great. Now, but you have to compare that number you mentioned to the amount of carbon we're putting up there, and the amount we're putting up there is pretty astronomical. So but there are technical fixes. It's just a question of the cost. You know, there are people who want to draw out, have windmills in effect that bring in the air with CO2 and capture the CO2 and make bricks out of it. You know, and you can do, that's possible, but it's going to be costly. And if you imagine, you know, the amount of carbon dioxide, imagine the weight of the fuel in your car. When you convert that from gasoline to CO2, its weight increases by more than a factor of 3, because CO2 is C12O16 times 2. And so we're putting a tremendous mass up there. If you want to, you got to make, just in running one tank of gas, you've got to make a lot of bricks. Thanks.
Thanks very much.